So this is 4.2 day 1, implicit differentiation. You're going to watch the video, taking notes as you would if this was me doing this live. And as you work through it, be sure to stop the video, figure out the problems, come back to it, see how you're doing, go back over parts of the video so that you get a thorough understanding. The implicit differentiation calculates a derivative for a curve that uses more than one variable. So a curve that might use more than one variable would be the circle that you can see. There's plenty of other curves. You can find the derivative without having to solve for y equals. So the reason it's called implicit differentiation is you're not moving it around to have the explicit or written out y equals function. You're actually leaving y in the function or whatever other variable and finding the derivative anyway. So the example that you see first is a circle. You had circles in pre-cal, so the equation x squared plus y squared equals 25 is the conic, the circle. They're asking for slope at an ordered pair. To find slope, we would find the derivative of the equation. We're no longer calling it a function because it isn't a single function. And then we would use the ordered pair 3, 4, so that at that point we found the slope or instantaneous velocity of the curve. In order to do that with implicit differentiation, you're going to keep the equation as it's written and take the derivative of both sides with respect to x. With respect to x means that when we hit y variables, we don't know the derivative because we don't know the y function. We're going to put in dy dx, meaning the derivative of y with respect to x in its place. So on this first expression, first equation, we've got x squared, and we know its derivative with respect to x is 2x. We don't know the derivative of the y function because we can't see its hidden values in terms of x. So what happens is we treat this like chain rule. We treat the y function like the u, and we'd say, okay, it would be 2, don't change the function, times the derivative of our embedded function. Our embedded function here is the y function, and we don't know its derivative in terms of x, so we have to say dy dx. That's the placeholder saying the derivative of the y function is, and the derivative on the 25 side is 0. In the equation now, as we see this, we're going to be moving this around so that we can get that dy dx, that derivative of y in terms of x, alone on one side. So a little algebra. Subtract the 2x on both sides. Do this with me. We have twice the y function times the derivative of the y function is negative 2x. Algebraically now, I'm going to divide both sides by 2y in order to get my derivative of y in terms of x alone. And it simplifies when I divide the 2's into the derivative will be the opposite of the x value over the opposite of the y value. Knowing that that's the derivative of this function, then I can go along and use that derivative in order to calculate the slope at 3, 4. So slope at 3, 4 of our circle up there, and what we're looking for essentially, and this is good calc notation, is we're going to use this derivative function with the ordered pair 3, 4 as our input values and tell what that's worth. So that calculus notation is worth seeing several times. It says the opposite of the x coordinate, so that'll be negative 3, all over the y coordinate, which is 4. So the slope at 3, 4 of the graph should be negative 3/4. I'm going to slide back up so we can look at the graph at the ordered pair 3, 4 and see if we think it's practical that the slope for that at that point should be negative 3/4. Okay, finish up that example before you, if you need to pause the video before you go on. Steps for implicit differentiation. I would pause the video here, record all of these steps so that you have them, and then we're going to go on with some examples. The first step says to differentiate both sides with respect to x. This is why we have to replace all of the times when we'd like to take a derivative of something that involves a y, and we're going to need to put the derivative of y with respect to x in that place, Or eventually you might sub that as y prime. We want you used to that dy dx notation. Step 3 hasn't come into play yet, if multiple terms. Step 4 will come in some of the examples, and then finally what we did was we solved for the y prime or the dy dx in order to have the derivative function. So pause here if you need an extra minute to get these steps down neatly so that you can use them. This curve's pretty cool looking, okay, and it is a smooth curve. There's no discontinuities like cusps or corners, so it's possible to differentiate the derivative at any point that doesn't cause a vertical tangent. So they like the slope at -2, +2. So looking on the curve, we don't have to be able to graph these in order to do the derivatives, but the graph's a nice visual. At that point, the slope looks like it could be 0, not sure. In order to tell, we're going to get the derivative of the function with respect to x. So we're going to take the derivative of both sides. So the derivative of the y squared side, chain rule says, would be 2y to the first power multiplied by whatever the derivative of the y function is with respect to x. And we don't know what the y function is in terms of x. So we just need to leave that as the placeholder for its derivative. The other side is exclusively a polynomial, and we know the derivative on that side, 3x squared plus 6x. We still then need to solve one side for that derivative function. So as I move this around, and I solve and I get that slope, dy over dx, I'm going to divide both sides by 2y. So my slope at any point on that curve then would look like that. They asked us to find the slope at a specific point, so I'm taking the derivative, dy dx, and evaluating it at the value -2, +2. And the derivative value at that location then would be 3 times the quantity -2 squared plus 6 times the quantity -2, all divided by twice the y value. Simplifying that all out, it comes up 0 over 4, or just 0. And it confirms for us that, in fact, the slope at that particular point on that curve is 0. So one of the last things before you get a chance to try some is to write an equation of the tangent line to this particular curve, same curve as last time, when the x is at -1. When you notice that the x is at -1 on this curve, most of the time you won't have the graph. We have the benefit of seeing that. There are 2 places where the x value has -1. So I'm going to bring over our derivative from the previous example because it was the same function. So our derivative from the previous example already tells us that the slopes, at least at those points, should be recorded as using this. But what we don't actually have is the entire ordered pair in order to get the slopes. The slope depends on both the x's and the y's. So what we need to do first is go back to the original function and find out at x is -1, what are the ordered pair values. So in the original function says the y values squared are, now my x value is -1, so at x is -1, I'm looking to find the ordered pairs for that graph. So it says the x value cubed plus 3 times the x value squared. And as you start to simplify that, you end up with y squared being 2, double check. So the y values when x is -1 are plus or minus the square root of 2. So the ordered pairs we're interested in finding slope out at are -1, negative square root of 2, and the other ordered pair here is -1, positive square root of 2. So when we write our tangents, we'll actually need 2 equations, one to describe each tangent. So we need the slopes then at each tangent, so we have our ordered pairs and we know for sure that our final tangent equations will look like this. One of them for this higher point will be y minus square root of 2 equals, I'll need the slope for that higher point, and I'm going to color it in green, times the quantity x plus 1, just using point slope. For the other one, we'll color it in red. For its equation, we already know the equation will look something like y plus the square root of 2 equals, we'll need the slope at that location, again, x plus 1. So I'm going to leave these over here so that at the very end we can just come back and put our slopes in and have our final equations. So to get the slopes at each ordered pair, I'll need to use the derivative function and evaluate it for that particular value of x and y. So as we do this, I'm going to start off at my -1 square root of 2 point. So to evaluate the derivative at that point, the derivative, which will give us the slope, is going to be worth 3 times the x value squared plus 6 times the x value divided by twice the y value. When you go to clean up the numerator for this one, you end up with -3 over 2 square roots of 2. We know we can't leave that square root of 2 in the denominator, so we're going to rationalize the equation, or the expression. -3 square roots of 2 all over 4 is the slope at the ordered pair -1, 2. So I'm going to come back, and it's for the green equations. So the green equation slope, -3 square roots of 2 over 4. All right, for the point that's in red, at the ordered pair -1, -2, negative square root of 2. I need the slope. Same process, I need to evaluate the derivative at that point. So the derivative evaluated at that point is going to start off an awful lot like what we had before. In fact, the exact same numerator because the x value has not changed. So it would be 3 times the -1 squared plus 6 times -1. So the numerator we already know is going to be -3. The denominator wants twice the y value. And so twice the y value here just ends up being twice the 2 square roots, or twice the square root of 2. Square root of 2, and this one's negative, so we end up with a negative denominator. So the difference here when we clean this one up is we're going to get the opposite. We're going to get +3 square roots of 2 all over 4 for the slope for that one. Putting that back in, 3 square roots of 2 over 4. So our 2 tangent equations to the curve, the red one definitely makes sense to have a positive slope, the green one definitely makes sense to have a negative slope. Remember to pause the video, do some of this, check it, slow it down, go back over things. So I'm going to pause the video right here, stop it. You're going to try these two, and then the next video clip will pick up with us going over these and seeing how you did.